Midterm. So last time in our last exciting embedded microcontrollers class, we were covering homework 7 on sampling and program memory. I think we got up to question number 25. Do we need to finish coverage on homework 7? I think it's due tonight. Anybody need any additional assistance with homework 7? Because if not, I'm going to swoop into the midterm. Any questions left for homework 7? You've all submitted it already, or no questions? All right, then let's move on. I'm going to move on to the midterm, and I'll be able to answer any questions you might have about the midterm. We wait for confirmation. What? Oh, apparently when it's long, it doesn't. Close window. Can I close the window and still keep this open? Close window. No. Darn it. It's a Blackboard thing. He makes you look at this submit thing. All right. So bottom line, this is a mashup of your prior homeworks. Also, I'm going to be called away on business this coming Monday. So I'm going to give you a pre-recorded lecture to watch Monday. So this is your chance to ask any question you like. And what I'm going to do is see how quickly we can do I'll call it a breadth first coverage of the midterm. And as I scroll through it, take note of any particular questions you think might be challenging. And then I'm going to go back to the beginning, and I'm going to have you go and ask me questions about things that look like they're unfamiliar or you don't quite remember. But in general, every question that you see in this midterm is a question that you've done before. It's taken from prior homework. So this is a comprehensive midterm covering prior homeworks, put it to you that way. Open book, open notes. You get 2 stabs at it. You get the highest grade of the 2 attempts. So if you don't like your first attempt, you can do it again. You can print the whole thing out and look at it and look at it offline. I've actually printed my copy. If you do want to print it, it's 40 pages, that's a lot. 52 questions, a lot of true, false, multiple choice, that sort of thing. And so without further ado, what I think I'll do is I'm just going to kind of do a quick first pass through the midterm, take note of any question numbers that you like, and then we'll go back over it. So this should look familiar to you. This is the A to D multiplexer registers and their meanings. And they figure prominently in some of these questions, but we just have to read the directions and figure out what they do, and we can fill out our little radio buttons. Let's see, what else do we need to know here? More analog to digital multiplexer questions. I think we've seen this in question 7. Let's see now. Here's yet even more analog to digital converter questions. Somehow they figure prominently here. Here's a little code for doing a fast loop back, which has the prescalers in it and all the other good stuff that we've been looking at from the past. And so we have some familiarity with that as well. And then some basic true-false questions about it. Here's another sine wave synthesizer. So we've seen that as well. And this one is interesting because we're using a sine table with a bunch of hexadecimal numbers that are essentially just a sine wave, and they're trading off space for time. I mean, this hardly saves you any time at all since we did all our computations in setup. So in fact, it just takes the same space as everything else did. And then let's see what else we got in here. Bitwise ands, shifting in the other direction, converting microseconds to sampling time, dereferencing pointers. That might be a little bit challenging for you guys. I don't know if you remember any of that stuff. Carriage return line feed, baud rates, information about bitwise exclusive OR. This is the DAC that we're using, the MCP 4921. If you ever have any questions about it, you can always look up the data sheet. Let's see now. There's some questions about code, a picture of our setup. Let's see now. Serial port usage, timer usage, 16 and 8-bit timer usage, basic C questions. Let's see now. What else do we got here? This is the same code that we've seen before with the prescalers being set. Let's see now. What's the maximum baud rate for my IDE? Well, you can just bring up the monitor and look. You'll know. Do bitwise inclusive or exclusive or. Oh, here's a good one. The rotary encoder. That might be worth going over. Let's see. That was question number 30. That's probably a good one to look at. And it's nice because it's kind of animated. Isn't that cool? I think that's sweet. And then let's see. Timer interrupts. I think we did something with interrupts and timers. You guys learned a lot today, this semester, for considering we did one interesting lab after another for 8 labs in a row. I thought that was pretty neat. Somebody asked, what happens after we go distance learning after Thanksgiving? And the answer is we're going to start using the simulator. So we'll do a deep dive into the simulator after Thanksgiving so you don't get too hung up on the hardware. Because hardware is too hard to debug remotely, I think. Let's see now, more information about sampling. Here's the first lab, which is a sort of a bit of a light show for us. And I think, lab number 1 was blinky light on steroids or something like this. Let's see now, question 37 is more about pointers. We got a microsecond question, which we probably know the answer to at this point. Masking interrupts, matching logical operations with their operators. Let's see now. This looks like more pre-scaling stuff. And here's an interesting C question. That you can't do this in Java, at least not directly the way they're showing. Here's a little bit of code for managing serial ports. Questions about your DAC. Questions about serial ports. More serial port questions. That's a good one. 46, we should go over that for sure. And the swapping question on page 47, we ought to go, on question 47, we ought to go over that. Let's see what else we got here. It's just some basic programming. Here's interesting information about the Watchdog Timer. Now, that might be a little bit new for you guys, so we might want to cover that one. Question 50, take note of that one. And let's see, what else do we need to do? That's about it. I think question 50 might be the challenge question because you'd have to actually use the web to look it up because I don't think we have any experience using the Watchdog Timer. But if you had any questions about something like that, Watchdog Timer on Arduino, you could just, I don't know, it's open book, open notes. So you can always read about it on the data sheet and for the Arduino. And there, you can read about it right now. In fact, you could say, what's a Watchdog Timer? What does that do? Oh, and then it's on the Unos, and there's all these other things that you can do with it. And basically, get something to go on in the background to wake up your Arduino in case it's time. Let's see. Yeah, so here's a little oscillator and a prescaler, and it looks like it'll do an MCU reset or an interrupt Watchdog Timer. So just another timer with some prescalers on it. I never use it, but it's there. It's there for you to use. It's part of the hardware built into the chip. And yeah, that's kind of neat, actually. Use it for an interrupt. Use it to reset the computer. What you could do with the Watchdog Timer is have it automatically reset your computer if you don't reset the timer. So you could say every 10 seconds, I'm going to reset this timer. And then if your program gets hosed and you don't reset the timer resets your whole computer and gets you to restart again. So it kind of keeps track of, well, it lets you guard against your program kind of getting stuck in a deadlock. So that's kind of cool, actually. So that's the test, such as it is, and that's our first pass at it. And now I think what I would do is I would open the floor to questions. And you may type them into the chat if you like, or you can just shout them out. I'll just go through this. See if anybody wants to stop me. Here's question 2. Question 3. Question 4. I think we've seen all of these things already. Here's the loopback code that we saw from before. And here's playing a sine tone. I think we got our fill of sine tones from this board last time.
Professor?
Yeah. Yeah, which number would you like to do?
This really isn't what the question is asking, but for question 30, the Arduino rotary encoder, what is it being manually rotated, like by a person, or is it being done electronically?
See, this is the shaft for the rotary encoder, and it takes a knob. But what you can do if you wanted to measure the number of times a shaft turned on a motor, an electric motor, in order to measure how many times it's turned, is you could effectively determine how many times the wheel has turned, and in which case you've built a kind of an odometer. And so the odometer represents an internal sensor. You can also use it, for example, on a DC motor, which doesn't, not a servo motor. And essentially, because you've got that feedback available, it becomes a servo motor. So if you think about it, you could take a giant AC motor. It's not meant to be controlled by a computer at all, from a dryer or something, like a real clothing dryer, big motor, quarter horsepower motor, and put a shaft encoder on it. And then you can measure how many times it's turned, and you can servo that motor with an external input. And that lets you determine how many rotations you've had, or you could even be more precise and just go part of a rotation. And this will help you to keep track of it. So you can use these in robotics. In fact, we have these gray code generators associated with DC servo motors that are mounted on the joints of various electric robots that we have on campus. So that's kind of interesting. So let's go back to the beginning. And I think we were kind of scrolling through question 9 and questions, about 10. Question 11, any questions? Questions about pointers? Pointer questions? Let's see. What else? Serial ports? Questions about serial ports? Or C questions? I mean, here's one, for example, the maximum baud rate for my IDE, what could that be? Well, I don't know. If I show a monitor, I can determine it's 250,000. Easy enough to find out. So let's see, bitwise, inclusive OR, shifting. There's a little gray code encoder. Question 31. Oh, I'll try this on you. What do you suppose the answer is to question 31? Can we expect the timer interrupt service routine to be called every second? Is that what this is? A million something or other? A million microseconds? I think that's question number 31. Is that true or false, do you think? We actually did this. You know, this was from a homework. So that, yes, indeed, is in microseconds. And we would expect that this interrupt service routine in here will be invoked every million microseconds. To within plus or minus 4 microseconds, because I don't think it's very accurate. Well, 4 microseconds is pretty accurate, actually. Let's see. We've done bit manipulations. Well, here's one. If we sample at 220 kilohertz and we put in 512 samples into our sine wave, what will the output frequency be? How would you approach solving that problem?
Is it the frequency divided by the sample?
Yep. So that comes out to be about 433 hertz, which is 222,000 divided by 512, and, well, 433.59, so that's 434. So that's a pretty low frequency, but it's a precision sine wave, which may or may not be of any interest. Let's see what else we got. How about this question 37? Is this declaring a pointer to an int? What is this star IP? Anybody know? Somebody wrote question 36. I'll go back. I'll do that. But first, let's take a stab at this one. Does that declare a pointer to an int? What does IP stand for? I don't see anything in the chat. You guys are just going to sit like lumps on bumps on me. Is that it? It's a yes or no question. It's true or false. It's just like digital design to ask a true false question. Because in computer engineering, everything is true and false, unless you're on a quantum computer, in which case everything is maybe. So any ideas? What does this mean? Pretend this is a Google interview test and you're trying to get that job at Google. And they say, well, what is this? And you go, I don't know. You think that's a good answer?
Is it false?
Now, actually, you had a 50-50 shot at that one. It's true. That is, that's going to be a pointer to an integer. So the contents of that will be an address, and you'll have to dereference it to get to the actual value. So that's an address. Let's do question 36 because someone asked. Consider the following setup. How would you write a for loop to light up the LEDs from left to right? So starting on the left and moving to the right. So they're all going to ground on one side. The other side, they go from 7, 6, 5, 4, 3, and 2. So if I needed a loop with I could say I equals 7. While I is greater than 1, I minus minus. It can't be done. I like that. That's a good answer. Can't be done. It's impossible. It's impossible. Here's one that's got a little timer in it, but he starts at line 2. Right? He's not starting at line 7. We're supposed to go from left to right. So that doesn't seem right. And here it is from 7 all the way down to including 2. And so that looks right to me. And here's one. Loop from the highest pin to the lowest. This looks right as well. Was it in there twice? Huh. This loops from the lowest to the highest and then the highest to the lowest, but the question just wanted you to go from left to right. From left to right. So it's got to go from 7 to 2. So that looks pretty good to me. Can't be this one. I don't think it can be this one either because he's going from 2 to 8. Over here he goes from 2 to 8. So what else do you want to know? Let's just scroll through some of these others. 38 micros, 39, turning on an LED. You can never mask an interrupt. Is that true? What happens if I'm in the middle of an interrupt and I get an interrupt? What do I do? Nobody has any idea?
Would that be false?
Yeah, that is false. You can mask an interrupt. If you do so, you may miss an interrupt. But in fact, by default, interrupts can be interrupted. So you could be in the middle of a long interrupt service routine and get another interruption right in the middle, and then you'll push your address to the stack, jump to the new routine that interrupted you, service that routine, and then when it returns, you pop it off the stack, and you'll be returning the program counter to your address that you left behind. So that is an interruptible thing unless you mask it. So interrupts can be interrupted by other interrupts unless you mask the interrupts, in which case they get serviced without interruption. And that's important, right? Because if you're in the middle of doing something time critical, like sampling an audio signal that has to go to the microphone, you don't want to be interrupted. I mean, you've got other things to do. You know, the Watchdog Timer, shut him up. Don't want to deal with him because you're busy. So I think we know what the different operations are at this point. These kind of look like Java operations to me. And what else do we need? Here's one we should use. So this is question number 43. Let's try and do some of the harder questions. I think that's a reasonably good idea. So what's the story here? We're trying to swap, right? Swap the values stored in address B and address A. So this is dereferencing. That's what this is doing. It's allowing us to take an integer, which is normally being passed by value, and pass it by address. You see, now we have the address of A and the address of B coming in. And now I can proceed to store A, get its value, swap A with B, and then get B out of the storage, from T. So that's a straight swap. You couldn't write that easily in Java, could you? Right? You'd have to have something like a first-class reference data type, like an capital I integer. Then you could do it. But you wouldn't do it by putting an ampersand in there. You would start with a reference data type. Let's see now.
Hey, Professor, I have a quick question.
Yes,
I
sir.
was slightly late to the party, so you might have gone over this, but question 14.
Oh, sure.
It
Sure.
kind of seems like there's something that's supposed to be there, like a line of code that's not.
Could be. Let's find out. Question 14, are we looking at now? Question 14?
Yeah.
Oops.
So it kind of looks like that's supposed to be talking about something, but I could be misreading.
No. It's missing the \R. That should say \R prints to the serial port as a human readable ASCII text followed by carriage return character and a new line character. That is missing something. That's a bug, and I'm going to make a note of it. We got to fix 14. Quote. For some reason, that got messed up in Blackboard. Maybe it doesn't like control characters. I think what it did was it just inserted. You know what it did? It inserted a new line. It saw the \R. It says, "Oh, that's a new line," and so it put in a new line. So, wow, bummer. Okay, we'll fix that. Sorry about that. So let's see what else. So we were up to question 43. We did the swap, right? And now here comes the serial port for 9600 baud. Do I have to do this at the start of every loop? This is question 44. I'm just going to zoom ahead here. So I need this at every
You
loop,
can,
right?
but
Well,
you don't
it has to
necessarily
be. It
have
says
to.
here. Yeah, it says it has to be used at the start of every loop. Well, actually, it says very loop. Oh, geez.
Oh, I filled that in my head too.
It's the very loop. What's a very loop? So let's fix 44 as well. That should say every. Not very. A very loop. Verily. And so the answer is no, you don't do this at every loop. You do it in the beginning, right? During the setup. You set up the serial port once, and then you just use it at that data rate. Now, could you change serial port speed in the middle of your program? And the answer is sure, you could. I don't ever do that. I don't think I've ever done it, actually. On the other hand, I have done it in my Java code. So here's an example. This is a Java program I wrote that does a serial port setup. And you can see you can change the serial port data rate. You can make it whatever you like. Well, up to a point anyway. And then in principle, this uses a USB to RS-232 interface called key serial. It's like a dongle that plugs into your USB interface. It gives you an RS-232. And then you can test your port. I don't know if you heard that, but it was auto dialing for me. That's like a Java program. And then you can go in here and you can set up your port and choose whether you want modem dialing or speaker dialing. And that kind of lets you use the computer to dial the phone and get through all that annoying voice jail, because nobody likes voice jail. So anyways, I haven't done that yet with the Arduino. I suppose I could, but so many things to do. So we know all about the 4921 now. You can always Google something like this and get the data sheet. In fact, that's a reasonable thing to do. Just, hit enter, and I imagine the data sheet is right here. So now you can view the data sheet and learn all about it. And he says he's got a 4.5 microsecond settling time. And that's what this says. Oh, it has a 4.5 microsecond settling time. Oh, it's true. It's true. See, because it's right there. Also, SPI interface is 20 megahertz clocks. Now, that's a little bit of a aspirational clock rate for a 16 megahertz Arduino Uno, right? You're not going to get 20 megahertz out of an Arduino Uno. It's just not there. But if you went to, let's say, a DUE, then yeah, that runs at a higher speed, and those things could give you that kind of speed, but not the Uno. Uno doesn't go that fast. But that doesn't mean the chip couldn't take it. At least this chip can take it. And that's the thing about SPI, right? I mean, it can give you a serial clock and you can distribute it across many chips, but you can't go any faster than the slowest chip. So if you've got, a chip that won't take 20 megahertz, then you're out of luck. You could probably just throttle the data rate down, something a little bit more reasonable. In serial communications, a stop bit is a framing bit. Framing bit. The number of start bits, the number of start bits is part of the specification. You need to do these things for asynchronous communications. Well, that's an interesting question, right? What is that referring to? Well, when I go into my serial port setup on my Java program, what do I see? Stop bits. Oh, that's interesting. Parity. Flow control. So these are all protocol, hardware protocol elements that you can set for the point-to-point protocol of the RS-232 interface. 8 data bits, no parity, 1 stop bit, and no flow control. 8 none 1. So let's take a look and see what that looks like. 8 none 1. So here's 8 data bits, 1 start bit, no parity, and 1 stop bit. So the start bit and the stop bit essentially tell the asynchronous communication interface adapter when the group of 8 bits begins and when the group of 8 bits ends. It needs to have that because what it'll do is it'll have an internal clock that resynchronizes based on the bit clock window coming in. So that's what the baud rate is all about. It's how many bits, or actually how many symbol changes you're going to get per second. And we need to know where to do our sampling. We want to sample in the middle of each one of these little windows here in order to be able to make sure that we can know whether we're getting a 1 or a 0. If we're off, we're going to have a framing error. So in serial communications, a stop bit is a framing bit. So it helps to frame the bits, groups them together. The number of bits as the number of start bits is part of the specification. That's correct. Right? Because why? Because we need to know how many start bits, stop bits, and parity bits we're going to be using if we're going to have reliable communications between one point and another. So that was question 46. Why does asynchronous RS-232 serial communication need framing bits? Why is that?
Because it's a stream of data, and otherwise you would never know where a single message starts and stops within the stream.
The key is asynchronous. You know, if you had a separate clock, like for example, SPI has a serial clock, well, that is a synchronous communication system. So we don't have to have framing bits for SPI. We have a clock that will tell us when we should sample the incoming data bits. Because if we sample them at the wrong place, we might sample bit 0 where we have bit 1 coming in. So knowing, you know, the whole point of having an asynchronous communication system is it saves you a wire. That one wire which distributes the clock is not present, but it costs you, right? The cost is this overhead and start bits, stop bits, and parity bits. And that overhead is substantial, right? Because right here we've got 2 bits because start and stop. But if you had a parity, then it'd be 3 bits. So you'd be sending 3 bits worth of data for every 8 bits that you want to transmit. So in effect, you're transmitting 10 or 11 bits for every 8 bits that are going out the door.
And it changes your code complexity, because if you're framing, you have to check for all those start and stop bits.
Yeah, presumably that's right. I mean, you would either put that in hardware or you would put it in software. And if you put it in software, it certainly increases complexity. If you put it in hardware, you know, from a programmer point of view, we kind of don't care. And in fact, if you put it in your libraries and software, it might slow things down a little bit, but in principle, you shouldn't see the complexity. But hiding the complexity doesn't really make it go away, it just hides it. So here's a question 47. See, here's a swap function. This looks like we're going to store the address here, then swap addresses, and then restore the address to the other variable. And then here's another one. And this says main A20 equals 23, B equals 47, swap A and B. Here's the swap function. The above value will swap the values. The above code, the swap code, will swap the values of A and B. Is that true? This is question number 47. Well, are we calling by name or are we calling by reference? What's going on over here? So that's a pointer, right? And so now we have some sort of a value which we're going to dereference and get the address of that location so we can pass it into this pointer to an address of int. And then what it'll do is it'll go through and do its little swap routine. Not an easy piece of code to write in Java. Not like this. So there's question 48. I think we're getting pretty close to the end of this thing, right? How many questions are there? 52. Any questions about 48? Question 49? Any questions?
I have a question a little bit earlier in the exam.
Okay.
So question 42. Now, should that negative sign in front of PS 128 be a tilde?
Question number 42. Let's have a look. Negative sign. Negative sign. Where am I seeing a negative sign?
Next line. Scroll down.
Oh,
so it's showing up as a tilde as a negative. Oh, you have to zoom way in. Wow, that's crazy. So when it first shows up, it looks like a negative, but if you zoom way in, it turns into a tilde. So I guess that was just my question.
Yep.
I'm good then.
Okay. What else? We were busy doing question number 46. I think we kind of covered the serial port thing, the asynchronous. That's kind of done. Then we had the swapping question, and I think we got past 48. If somebody has a question. Here's 49. And there's the Watchdog Timer we talked about earlier. Often used to automatically reset an embedded device that hangs because of a software or hardware fault. You know, what I'm reminded of is sort of like the lawyer that has the goods on everybody that you've blackmailed. If anything happens to me, you can send this to the newspaper, right? So this is what happens, right? You know, something happened to your computer and it died, and the Watchdog Timer says, ooh, I haven't heard from you in a while. So then it says, okay, maybe it's time for a reset. And then it goes and shuts you down and wakes you up again. So that's very good for a mission critical application, I think, where, I don't know, I'm trying to think of a mission critical application where it's okay to reset the computer. Probably not on your Ariane 5 booster rocket, but maybe somewhere else, a little less mission critical than that, unless there's a backup computer. I suppose that's okay. If it's your guidance computer and you've got a $500 million payload, you probably don't want to reset it. I'm guessing. But maybe if it's Ardu pilot and you somehow, I don't know what could happen. Oh, I know. You take Ardu pilot and you launch it into a weather balloon, and it's 95 miles above the surface of the Earth, and it's minus 60 degrees. And your Arduino just got froze up. And your GoPro camera doesn't work real good at minus 60 degrees because batteries don't like it. So then on the way down, things warm up, and the Watchdog Timer says, wake up, wake up, wake up. And it's like bitchin' Betty going, oh, and the Arduino says, yeah, I'm awake. And then it wakes up and says, okay, better contact mission control and let everybody know that I'm back.
Or if you have like a power tool or something that has a short that can hurt you if it goes wrong, like it'll usually watchdog itself and
Yep. Something
Turn off.
something will overheat. Maybe some sort of a thermal fuse, and then after it cools off, it restarts. Hair dryers have that sort of thing, you know. Let's see, question 51, but that's completely electromechanical, right? That's not a
not a
computer.
microcontroller in that case.
Yeah, no, but it's a good idea. Do it with a microcontroller, I guess. Let's see. True or false? The above code will print out the number and 0 unless no line ending is used. The number or 0. So here comes somebody inputting a number called parseInt. And now it says here it's going to output the number in decimal. So it looks like a 0 comes out too. So in comes, look for the next valid integer in the incoming serial stream. So somebody types in 1, and then this thing prints out the 1 and then a decimal. Let's see, the above code will print out the number and 0 unless no line ending is used. No line ending.
It'll print the number, but it won't print a 0, right?
I think it is going to print a 0. But if you ever had a question like that, you could probably copy this and put it into your friendly neighborhood IDE. Oh, and you'd need a computer. I don't have a computer hooked to my computer. So that's not going to work. Oh, I know what you can do. You could run it in a simulator. So you could do Tinkercad. Didn't think I'd be using the simulator today. Let's see. I've got, well, here's my thermocouple. Let's see. I'll just tinker on it. Oh, it's taking its time. I wonder if Zoom slows everything down. So let's do this. We're just going to grab the code, and I think I can just wipe this out and put in the code I was interested in. And this is going to look for a 9, enter. It didn't do anything. Oh, look, it printed out a 10, a 9 without the 0. So let's see now. Look for the next valid integer coming in, and then it does a print. What if I put in 90? Gosh, that's slow. So that seems to work. What if I put in which is not an int? Oh, puts out a 0. That's cool. Figured it would throw an arithmetic exception at runtime like Java. Nope. Just fails. So that's a that's a good way to find an answer real quick, and you don't even need a computer to do it. Well, you don't need an Arduino Uno to do it. Put it another way. You can do it in simulation. Can I close this? So the above code will print out the number and 0 unless no line ending is used. I'm going to say that's a false. But now that I look at it, I see there's a bug in my answer key. That should be false. So, question 51 needs to be fixed. I'm finding bugs. So I found a bug in question 14. question 44, question 51. Another bug. Have people already taken this test? As I saw, somebody had done some attempts, but I'm going to change
I
that.
just noticed those because I'd run through the questions, but I didn't submit it.
Yeah, hopefully you didn't submit it because I think I need to fix that answer key.
I did not.
I will do that by the beginning of my next class, which is at 2 o'clock. So this class ends at, perhaps 20 minutes. So, yeah, we still have a little time to go over this midterm. Let's see what else we got here. If the serial is available, read the incoming byte. Say what you got. I received a B and it prints it out in decimal. This prints a decimal version of B. True or false? This is one of those, you could certainly take this and cut and paste it and put it into Tinkercad and try it. Although from what I just saw, it's actually faster to hook an Arduino up to the computer and do it. But maybe it's convenient to have something like Tinkercad around just so you can run simple programs like this. So any ideas? Is that true or false? No.
Is it true?
Yeah, that's true. We're going to get the decimal version. I could print out the binary version or the hexadecimal version, but that's, yeah, this is for decimal. DEC is for decimal. And that is the test. Such as it is, we can go back over anything you like. Want to go back to the beginning and just sort of quickly zip through it again just to make sure there's nothing tricky here. This is pretty straightforward stuff. Stuff you've seen before. I think you guys are now experts. So let's see now. We know how to read data sheets. I think that's good. Actually, that's very good because you'll be needing to know how to read a data sheet throughout your adult professional career as you go and explore new hardware. So I guess maybe the message of interfacing everything to everything is read the data sheets. Let's see.
Can you go over one?
Question 1. Sure. Let's do question 1. So question 1 is asking, let's just read the question here. Given the AD mux description, which is here, which setting makes the ADC most sensitive to low input voltages? So that is a question about the voltage reference selection bits. That's what that's about. So let's see what we can do. If I have an internal 1.1 volt reference, that's going to make it more sensitive than if I use VCC, because VCC is like 5 volts. So if my full scale deflection is 0 to 5 volts, then and if I have an ADD converter that's, I don't know, 1024 levels, then I will have 5 divided by 1024, which is equal to 4 millivolts, 4.8 millivolts. But if I make my full scale deflection 2.56 volts, 2.56 divided by 1024, that gives me 2.5 millivolts. And then if I go to 1.1 and divide it by, I don't know, 1024, then I'm down to 1 millivolt. So clearly things are more sensitive with 1 millivolt. So 0, 1, 0, setting REFS 1 and clearing REFS 2 and 0 should make things a little bit more sensitive. So 101, which is looking an awful lot like this, will make things more sensitive. Let me see if I got that right. I'm looking at my answer key. Yep. Yep. That's correct. So, and it's an internal voltage reference. So that's kind of convenient, right? Because maybe you would like to have a high sensitivity input because what you've got is a relatively low output, perhaps from a microphone or a guitar or something like this. Guitars are usually 1 volt peak to peak, maybe less, probably less. Well, actually, guitars without any preamp will be in the millivolt range. Let's see what else we got here. So a lot of these things, like for example, will this use the most significant byte first? So here's 80 mux, and he's going 0, 1, 1, and then all zeros. So take a look at the 80 mux data sheet, which is over in here. 0, 0, 1, 1. So 80 LAR is going to be a 1. And you should be able to figure out what that means by looking at the data sheet. Is 80 LAR defined anywhere? Oh yeah, here it is. Here's references. If you have any questions about what that does, you can always use the Google because it's open book, open notes. So do a quick ADLAR on the Mega 328. You can get some information about that. I kind of mislaid it just now. Oh, this is much nicer. I like this. I like this little picture. Isn't that nice? That's nice. Somebody really thought about that. So somewhere in here, it should say something about the ADLAR, and there it is. And so if it's low, you get this. If it's high, you get that. It looks like the most significant bits go into ADCH. And you get 2 least significant bits in ADCL. And I forget the question. This has the most significant byte first. So setting ADLAR, question 4, will give you the most significant byte first. And you can see that if you look at the data sheet. Here it is, most significant byte comes in first. So any other questions? No questions? Really?
We could look at problem 29.
All right, let's do that. Question 29. In the following code, what's happening here? What does this do? What is this doing? What is this? Who writes code like this? Sneaky professor code. That's what that is. Sneaky professor code. SPC. Sneaky professor code. SPC. That's good, right? Sneaky Professor Code, SPC. What is this code doing? Well, what is the binary representation for hexadecimal 80? This right here. What is this? What is that? The answer is, here, I'll just type it up in here. It's a 1 followed by, I typed 2. Wait, a 1 followed by 7 zeros. 1, 2, 3, 4, 5, 6, 7. Right? Now, if you shift it, why doesn't this work? Shift it by 1 bit, the output will be 0, 1, followed by 6 zeros. 1, 2, 3, 4, 5, 6. And then if you shift that by 1, the output will be 2 zeros, followed by a 1, followed by 5 zeros. 1, 2, 3, 4, 5. Right? In other words, that's going to keep doing that until eventually, ... you'll have 1, 2, 3, 4, 5, 6, 7, and then a 1. And then it'll all be 0. 2, 3, 4, 5, 6, 7, 8, because you keep shifting. So you're shifting the 1 over. So it's going to keep going down by an order of magnitude. No, by it's going to keep dividing by 2. That's what it's going to keep doing. So then it says here, the following will be the values of the bit being like this variable in here. 1, 0, 0, 0. Then it says 0, 1, 1, 1, 1, 1. 0, 0, 1, 1, 1, 1, 1. So this is question 29. Do you think that's what happens there? And you can see from here, no, that's not what happens, right? Because it's just doing a shift off to the right, and the zeros are not wrapping around or turning to 1s or anything. So in effect, what this is doing is it's just taking 1 and shifting it. It's a shift register. And it's shifting the 1 until there's nothing left but 0. And this says while bit, right? So this has to be while bit is something other than 0. So once it becomes 0, this thing stops. And so this is not correct, what we have here. That's not what it's going to do. So the answer there is false. Do people kind of see that? We could write code for this, I suppose. I guess it's another Tinkercad exercise. I don't spare me on that one. Does it make sense? Are people clear on this?
Yes.
Okay, good. Thank you. What other questions shall we try? Sort of zip through the test again. Easy test. Easy professor. Happy students. Anything else? Want a little lecture on NRF 24 LO1s? That's always fun. I should spend the rest of the class on this midterm because that's what's important to you. I know, because I used to be a student and things like midterms always stressed me out. Any questions so far? I mean, I guess we've scanned through this like half a dozen times already. And you guys are notably silent. So for something like this, if you wonder what it does, you could always just kind of plug it into your simulator and run it. What does that do? What will the output be? Well, let's see. Does this have a new line? No, no line here, but what about this? This has a new line. So it's going to print out I equals, and then the value of I, and then a new line. So we know it's not this, and we know it's not this because Arduinos do have print statements. And now we see something that looks good. And we see something again that looks good, only this one ends in 10, and the other one does not. It ends in 9. So those are different. When will this loop end? And look, it's less than 10. So it's going to have a new line each time, and it's going to end with 9. So that's that. Anything else? Well, I don't see any point in trying to do a lecture on new material because we've got maybe 5 minutes left. But I would like to make sure that you guys have all your questions answered on this midterm before we sign off. Anybody have any other questions they'd like to ask about the midterm? Ask me anything. Or at least ask me anything about the midterm. No questions? Going once. Going twice. Going 3 times. Okay, then. I guess we don't have any more questions about the midterm, so I'm calling it. We're going to end class just a little bit early. Here's my clock. So what we're going to do is, if you have any questions, we can try and cover them at the last minute on Thursday, but I will not be here to give you an in-person Zoom lecture on Monday because of, because of a business requirement. So sorry about that. But if there are any last minute questions that you have problems with, let me know. And I'm going to get the questions number 14, 44, and 51 fixed very soon now. In fact, I'll work on that within the next 20 minutes. We'll have that fixed. I'm pretty sure. So if there are no more questions, I want to thank you very much for your attentions, and good luck with the midterm.
Thank you.
Thank you.
Thank you.
Have a good one.